Hello all. Let's solve the GATE 2020 aerospace questions related to the topic aircraft performance in this video. Okay. Without any further delay, let's get into the solutions. So let's start with the first question now. So which of the following statement is or true? So this is kind of, you can have multiple answers for this question. So you don't need to restrict yourself with only one option for this question. So for that, we need to go through all different answers or the options that is given the question, and let's see let's validate the truth of that statement. Then we can come to the conclusion. So let's start with the first option. The first option is service ceiling is higher than the absolute ceiling of a piston propeller aircraft. So for this, we need to know what is the definition of service ceiling and what is the definition of absolute ceiling, right? So absolute ceiling is nothing but the height at which, so absolute ceiling is nothing but the height at which the, the aircraft will have zero rate of climb, which means the aircraft cannot go above that height or above that altitude. So which means your rate of climb R by C, which is called 0, okay, feet per minute. So it cannot even go above that altitude. This is not just for piston propeller aircraft, this is true for any aircraft. And then coming to the service ceiling, right? So service ceiling, that by the definition of that, it is nothing but the rate of climb is equal to 100 feet per minute. So per minute it can go to, at maximum of it can reach 100 feet. So service ceiling is something below the absolute ceiling, right? The reason is, if it is above the absolute ceiling, then it cannot even climb further, right? But by the statement of absolute ceiling is an height where the aircraft cannot, the rate of climb of the aircraft is zero. Say for example, if this is some altitude and this is some altitude, so service ceiling will always be lower, because that from there the aircraft has some scope to go further in height. Whereas absolute ceiling, the aircraft does not have any scope to go altitude, further in altitude, because the definition of absolute ceiling is the rate of climb is equal to 0, whereas the rate of climb is 100 feet per minute in service ceiling. So obviously, service ceiling will be lower for any aircraft than the absolute ceiling, but it is told in the statement service ceiling is higher. So this statement is not true, wrong. Let's move on to the second statement. For a given aircraft, the aircraft speed increases with increase in altitude. So stall speed increases with increase in altitude. So let's get the expression of stall speed. So now let's take the aircraft is at cruise or level condition, or any maneuver should also do, but let's take with that. So at cruise, L is equal to W. So what is the formula for lift? L is equal to of rho. So they have asked about stalling speed, right? V stall. So I'll put Vs. Vs stands for stall of rho Vs square. S stands for the surface area, and CL max, because during stalling you'll get the CL max. Now during cruise, L is equal to W. So you can equate this to W. From here, if you get the stalling equation, Vs is equal to root of 2W divided by rho S CL max. So CL max corresponds to stalling speed. Now if you see, you have got the expression for stalling velocity. For a given aircraft, the stall speed increases with increase in altitude. Yes, right? Because if you increase in altitude, provided everything else is same, like weight of the aircraft, surface area, CL max and everything is same. If you increase in altitude, the atmospheric parameter density will decrease, right? As H altitude increases, rho will decrease. That we have studied in atmosphere relationships, right? So for that, you can refer the advanced flight mechanics demo class in the channel. So this will come down. So what will happen, as altitude increases, your density will come down. Density is in the denominator for the velocity expression, stalling speed. So when density decreases, the velocity will go up, right? Because it's in the denominator. So as rho increases, V stall will increase. Rho decreases, V stall will increases. So that statement is correct. Okay, the second statement is correct. Now moving to the third statement, everything else remain the same. The tailwind increases the range of an aircraft. So for this, we need to know the definition of range first. So here you have to be a little careful here. What is the definition of range? Range is defined as the the horizontal distance covered in the ground. That is very, very important. For example, if an aircraft is flying from this point, so this is the aircraft starting point, let's put this one, and it is flying all the way and it is reaching point 2. Okay, and it has reached this point. Let's assume like that. Okay, now the range is always covered in such a way that the horizontal distance that has been traveled by the aircraft, and the horizontal distance is measured in the ground. So this is the horizontal distance. Okay, this is called as range, not the range over the air. Okay, it's always, the range is always calculated in the ground, with respect to the ground. With respect to the land, how much distance it got covered. Okay, so what is the range formula is for a, yeah, for an aircraft generally? So the range is nothing but R is equal to CL by CD. I'm writing the general range formula. So it will vary for jet and piston engines. But generally, what I'm trying to say is velocity is directly proportional to range. Generally, velocity is directly proportional to the range of the aircraft. So that's how you have to keep it in mind. So range is equal to VG. VG stands for velocity at the ground, or the ground velocity, CT. So ground velocity is nothing but if you measure the velocity of the aircraft by standing in the ground. So your reference frame is, your fixed reference frame is from the ground. So that's called ground velocity. Generally, we put V infinity. If there is no wind, right, either tailwind or headwind. If there is no wind, obviously V infinity will be Vg. V infinity is nothing but the speed at which the aircraft is traveling. Vg is nothing but the speed that has been measured by a standing person in the ground. Okay, this, for example, the speed that has been experienced by a passenger who is sitting inside the aircraft is V infinity, the speed at which the aircraft is traveling. But the speed at which the aircraft is traveling is measured from a person who is standing in the ground. He will see Vg. Vg is nothing but the speed of the aircraft from the fixed reference frame. From the moving reference frame, the speed of the aircraft is V infinity. If there is no wind, either tailwind or headwind, no wind, Vg is equal to V infinity. If there is wind, if there is a headwind or tailwind, so for, in this case, tailwind is asked in the question. If it's a tailwind is there, what will happen is Vg is equal to V infinity plus V tailwind. So what is tailwind basically? If the aircraft is moving forward like this, right? So the speed at which it is moving, this aircraft velocity is V infinity. Already some tailwind is pushing this aircraft like this, VTW. So now the ground velocity is, the person who is standing in the ground and watching the aircraft will feel that the aircraft is moving at a speed of V infinity plus VTW. But the person who is sitting in the aircraft, inside the aircraft, will only feel the velocity, the speed of the aircraft is V infinity. Okay, so that's the difference. So now the range formula, general range formula is Vg by Ct into CL by CD ln W naught by W. But if you see here, Vg is directly proportional to range. So from this equation, you can write R directly proportional to Vg. And if tailwind happens, Vg will increase, right? If there is no wind, Vg is equal to V infinity. If there is a tailwind, Vg is equal to V infinity plus VTW. So obviously, as velocity increases, ground velocity increases, range will go up. So if there is a tailwind, the aircraft will cover more range. So the third statement is also true. Okay. Now, for a jet aircraft constrained to fly at a constant altitude, for some reason, a jet aircraft is flying at a constant altitude, there exists an altitude where it can get maximum range. So this is very straightforward. For a jet aircraft, let's see what is the brigade range equation. So range of a jet aircraft is, we have already studied this, the class. So range of the jet aircraft is 1 by C, CL power 1 by 2 divided by CD into 2 into root of 2 by rho S Rho is density, S is the surface area, into root of W1 minus root of W2. So remaining, keeping everything constant, range of the jet aircraft is dependent on the altitude because rho dependent on rho. If you increase your altitude, rho will come down. If rho comes down, rho is in the denominator. So our jet will go up as rho come down because rho is in the denominator. You see rho is here, rho is in the denominator. So for a jet engine, there exists a higher altitude where the range can be maximum or increased. So option 4 is also correct. So the answer for this question is option 2, 3, 4. Okay, 2, 3, 4. All the three are right statements. Okay, so this is a very easy problem. It's a numeric problem. So let's first write what are the things that has been given in this problem. Okay, so the weight of the aircraft is given. So W is equal to 10,000 kg. Okay, weight of the aircraft is given. And then if you want to convert, so actually this is not a weight, this is mass actually. If you want to convert to weight, you have to multiply with the acceleration due to gravity, which is g, and g is given. They have asked g to taken to be 10 meter per second. So instead of g, if you substitute 10, it will be like 1 lakh Newton, right? So the weight of the aircraft is 1 lakh Newton. So now they have also given an elliptical wing, which means the Oswald efficiency factor E is equal to 1, and with a span of 10 meter, which means span means B is equal to 10, and the area is nothing but the wetted surface area, S is equal to 30 meter square. So this is 10 meter, and then they have given the profile drag coefficient, which is CD naught, which is the profile drag coefficient, which is 0.025 they have given, and the maximum speed of the aircraft in a steady and level flight, which means they have told the aircraft is at a cruising condition, and V infinity is equal to 100 meter per second. So that also they have given. So now they have given the density of the air at sea level, which is 1.225 kilogram per second. So now what are they asking? The maximum thrust developed by the engine at sea level. Okay, if the aircraft is having these kind of characteristics like 1 lakh Newton of weight, Oswald efficiency is equal to 1, span is equal to 10 meter, surface area is equal to 30 meter per second, CD naught, its profile drag coefficient is 0.025, what would be its maximum thrust? So we all know that the thrust at a cruising condition, right? At cruise, we all know that lift is equal to weight and thrust is equal to drag. So now if you calculate your what is your drag, that will be your thrust, right? Because it's a cruising condition, steady and level flight is given in the question. Okay, now if you calculate your drag, that will be your thrust. So what is the equation of drag? D is equal to of rho V infinity square S CD. So rho is given in the question. Yes, we have got rho V infinity is given 100 meter per second. Surface area is given. S has been given. S 30 meter per square. CD naught is given, but CD is not given. CD is the total drag coefficient, but CD naught is given. So we have to find out CD naught. If you find CD naught, CD, then we can substitute CD here. Then that's the answer. So for that, what we can do to how to find CD naught? So using the drag polar relationship, CD is equal to CD naught plus KCL square, right? So which is nothing but what is CD naught, which is given 0.025. 0.025 plus K is nothing but 1 by pi EAR, right? So CL square into 1 by pi EAR. So pi is pi into E is 1, Asphalt efficiency factor, because it's an elliptical wing. Aspect ratio, how do you calculate aspect ratio? So aspect ratio is nothing but B square by S. AR aspect ratio is equal to B square by S. So B is given, S is given. So what is B square? B square is nothing but 10 into 10. So which is 100 divided by 30. So if you substitute that, you will get 100 here divided by 30. So basically 10 by 3 will come. Okay. So now In this equation, to get the CD and substitute back in the drag equation, you don't know what is CL. That is the other challenge you have. Then you have to find CL to calculate CD. Once you calculate CD, then go back and substitute in your drag equation, calculate the value of drag. That is nothing but your thrust at the cruising flight. So how to find out CL? That would be the next question, right? So for that, we have to use other information because it's a cruising condition, right? So I already told L is equal to W. What is the equation of L? L is equal to half rho V infinity square S CL, which at cruise, which is equal to W, right? So this can be equated to W is 1 lakh Newton, right? That we have already seen. 1 lakh is equal to half. Rho is nothing but 1.225, which is given in the question. V infinity square is given. I think it's 100 meter per second. So 100 square into S is given 30 into CL. So the only unknown in this equation is CL. Now if you write an expression for CL, CL is equal to 2 into 1 lakh Newton of weight divided by 1.225 into 100 square, which is nothing but 10,000 into 30. If you substitute this, if you get the answer, the value will be for the CL is 0.544. So the CL is 0.54. Now if you go back and substitute your CL value in the CD equation, which is nothing but CD is equal to 0.025 plus 0.544 the whole square, CL square by pi AR. So pi into 1 into AR, we found it to be 10 by 3. If you substitute, your CD will come out to be 0.025 plus 0.028. So this value will, this entire value is nothing but 0.028. So your CD is nothing but 0.053. So now you have got the CD. Now the whole idea is to calculate the thrust here, right? So thrust is equal to drag. So we have already figured out the equation of drag. D is equal to half rho V infinity square. So we know everything except CD. Now we have found out CD. What is CD? 0.053. So drag is equal to half into 1.225 into V infinity square is nothing but 100 square into S is 30 into CD is 0.053. If you substitute, your drag will come out to be 9738.75 Newton, which is nothing but your thrust in cruising condition. So the answer is 9738.75. The answer might go here and there because of the way we do use the calculations and all, but this is the answer. Okay, moving ahead, let's go to the third question. So this is also again an easy problem. This is one of the a numerical problem again. So let's write what are the things that has been given in the question. So it is given that the wing loading of the aircraft is given. Wing loading is nothing but weight by surface area. W by S is given 1800, so which is 1800 Newton per meter square. So wing loading is given. Again, area is given. S is given, which is nothing but 30 meter square. Here, drag polar, the entire equation is given. CD, drag polar is given 0.02 plus 0.04 into CL square. We don't know the CL, so this is CD naught as per the drag polar equation. This is nothing but K. K is nothing but 1 by pi AR. Okay, that information is given. They have also told CL max value also they have told. CL max is equal to 1.6. And density at sea level is also given 1.225 kilogram per meter cube. So now what they are asking, the speed at which the aircraft achieves maximum endurance in a steady and level flight. Okay, so we have to find the velocity, the speed at which the aircraft needs to fly to reach to get the maximum endurance. So the aircraft is a jet aircraft. That is also an important thing here. So the aircraft is a jet aircraft. So endurance of a jet aircraft, we have already derived this thing in the class. So endurance of the jet aircraft is nothing but EJ is equal to CL by CD into log E W1 by W2, right? So if you want your endurance to be maximum, your CL by CD has to be maximum. If you want your CL by CD has to be maximum, we know that by the performance, drag has to be minimum, which is nothing but CD has to be minimum. So drag has to be, which is nothing but then you have to fly at a velocity where you should get V minimum drag. So if you want your jet aircraft to have maximum endurance, you should fly at a velocity or the speed at which you'll get your minimum drag condition, because CL by CD has to be max, that corresponds to drag minimum condition, and the velocity that corresponds to drag minimum condition will give you the maximum endurance of the jet. So now how to find V minimum drag? So we know that we have already derived all these equations. During V minimum drag correspond to CL by CD max condition. So if you want to find out CL by CD, at what CL it will have CL by CD max is nothing but CL is equal to, this we already derived in the class, CD naught by K. This will give you the CL at which your CL by CD will be max. That will correspond to your V minimum drag. And now CD naught is given in the question. See, the drag plus 0.02. K is given in the question 0.04. So if you substitute that, what is CD naught? 0.02 divided by K. What is K? 0.04. So if you substitute, the root of 0.02 divided by 0.5 will give you value close to root of 0.5, right? Yes. So this is the CL. Root 0.5 is the CL. Now you have got the CL, but the answer we wanted to find out it, the corresponding speed. So how to find the speed? It's a cruising flight. We know that L is equal to half rho V infinity square SCL. So at cruise, which is equal to W. So now we have to find V infinity. So how to find V infinity now? So V infinity is equal to 2W. Let's write V infinity square 2W by S into CL into rho, right? So now this can be written as 2 into W by S into 1 by CL into rho, correct? So this is nothing but 2 into W by S is given 1800 in the question, right? Wing loading into 1 by CL. We have already just figured it out. What is the CL? Which is nothing but root 0.5 into rho. What is rho? Rho is nothing but 1.225. That is also given in the question. So this will give you V infinity square. Once you find out this, and if you take the root of this, your V infinity will be 64.475 meter per second. So the speed at which the aircraft has to fly to get the maximum endurance is 64.475. So you can write 64.475 meter per second. Moving on to the next question. Oh, this is an interesting question. So to solve this question, you need to know a bit of aerodynamics as well. You should have a good knowledge about aerodynamics as well. So it's a combination of performance plus aerodynamics question. Okay. So let's see what are the things that has been given in the question. So first, let's write the given information of the question. So it has been given that the weight of the aircraft is given. So basically the mass, because kg. So m is equal to 5500 kg. And if you want to convert this into weight, so w is equal to 5500 into, they have asked us to take g, use the value of g to be 9.81. So multiplied by 9.81 will give you the Newton. So w is given here. So mass is given here. And then it is given the pilot has initiated a steady pull-up maneuver, which means that even though the figure shows the aircraft is like this, it is going to take a path like this. Okay, it is going to take a pull-up path like that. So I will explain that how the flight path will look like. But the picture that they have given us at the lowermost part of the curve or part of the pull-up. Okay, I will tell you how the flight will move forward in the steady pull-up in a minute. First, let's write all the given information. So they're going to, during this steady pull-up, it will have a radius of curvature, right? The radius of turn, basically, the curvature. So that is nothing but 775 meter. I will explain this. What is this radius of curvature? And they have given the CG location here. They have given the CP location here, and they have given the tail CP. So this is nothing but the force at which the tail lift will act, the point at which the tail lift act will act. That is also given. So what are they asking now is, so they have asked to neglect the drag on the tail. So they have asked to neglect the drag on the tail, and also they have given that the thrust of the aircraft will be equal to the drag. That is also they have given. So it means that thrust and drag will cancel each other, and the drag part of the tail you can neglect. That has been given the question. Now they are asking, when they do the steady pull up like this, what would be the force for this aircraft, which is having a weight of 5500 kg and traveling at a speed of, I forgot to write this, traveling at a speed of v infinity is equal to 225 meter per second, and doing a steady pull up with a radius curvature of 775. If the pilot wanted to make this maneuver happen, the steady pull up maneuver happen, what would be the tail force? That was the question. Okay, they are given the CG information, CP location, and the distance between the CP and CG, and the distance between the tail and the tail point where the forces will act, and the CG location. So they have given CP location. So they have given everything on this particular problem. Okay. Now let's, before even solving this problem, let's try to understand how does the maneuver will look like. So the maneuver will look like this. See, this location of the aircraft is given in the question. You see, this is that location, the lowermost point, and it is going to fly like this. It is going to fly like this, fly like this. So I was talking about a radius of curvature, right, which is given in the question, 775 meters. So that is nothing but this. This is the radius of curvature. Okay, because it is going to any point. So it may be this one also. So it is going to take a steady pull like this. Okay, so that's the radius of. So it is not just as you see in the cruise, right? Cruise, or the only force that is acting downwards will be the weight. But if you see here, because the aircraft is in a circular motion, or it's going to take a vertical pull up, it is going to take this path. First, you need to know how to do the force balance. So at any given point of the aircraft, especially at the lower point, which is given in the question, right? Like this, your L will be balanced by both your weight and centrifugal force. Centrifugal force is nothing but mv square by r. So that is what this force, right? If you see here, mv square by r. So centrifugal force will always act opposite to the motion of the aircraft. So at the lower point, if you see, it will be opposite to the lift force, but as it takes the vertical loop, you see the centrifugal force keep on varying. So it acts exactly opposite to the direction of the lift, which is nothing but the perpendicular to the flight path. Okay. So now I hope you have understand how the vertical loop is taking place. Don't just get deceived by this figure alone, which is given in the question. That's why they have clearly told it's a steady pull up. The aircraft is going to take this path. Okay, but they have given the picture at this instant at the lowermost point of the steady pull up. So like that they have given. Now we have to know, asked, they have asked that what is the tail lift? Tail lift is LT. Tail force is nothing but tail lift. How does it get balanced? So now let's, using aerodynamics knowledge, we know that the definition of, what is the definition of CP, center of pressure point? The point at which the moment is equal to zero, right? The point at which the moment is equal to zero, right? So let's calculate the moment about CP and equate it to zero. Let's see, can we able to find out the tail lift? The wing lift will be here. That will be acting in the CP only, but that won't create any moment, right? The moment about that point will be always zero, right? So the wing lift will be acting at the CP, but we don't need to worry about wing lift because we are not going to calculate or get any moment using the wing lift, because the wing lift itself is acting on CP. So don't worry about it. So But now there will be two forces will be acting on the CG. So this is this point CG. One force will be weight of the aircraft. The other force will be mv square by r, which is nothing but the centrifugal force. You see, yes, that's what is case. W by g v square by r. Wv stands for m. Okay. So now the force balances is, so the force that acts on the CG is two forces. One is weight. So now let me write. So this is the point CG, and this is a point CP, and this is the tail point, which is LT. The force, both the forces are acting downwards. One is W, the other force is W by G so V square by R, which is nothing but centrifugal force, mv square by r. So now if you take moment about this point, this force, this total force W plus W by G into V square by r into this distance, and also moment about this point, the tail point, L into LT into this distance. So let's take moment about CG. Sorry, CP. Let's take moment about CP because we know that moment about CP is equal to 0 from aerodynamics, right? So what are the force that acts on CG? Weight plus centrifugal force, which is nothing but m v square by r into the momentum, the distance between the CG and CP, which is given in the question 20 centimeter. So which is 20 centimeter means 0.02 meter. Okay, but let's put minus sign because this force is towards the downwards and the lift force in the tail is towards the upward. So let's consider the downward force to be negative. Okay, plus now the moment about the CP because of this LT is, it's very straightforward. LT into the momentum distance is given 550 centimeters, so which is nothing but 5.5 meter, which is equal to 0 because the moment about the CP is equal to 0. That's what the definition of center of pressure from aerodynamics. Now in this equation we know everything. Weight we know, mass we know, LT alone we don't know. So we can calculate. LT is the question that has been asked, right? So uh, let's substitute weight. So weight is nothing but 5500 into 9.81 is weight, plus mass is nothing but 5500 only. V is given 225 meter square is given, divided by R is given the radius of curvature 775. Okay, into this is the force that is acting on the CG. Generally the force that will act through the CG is only weight, but since the aircraft is going to take a pull-up maneuver, now the force is weight plus centrifugal force. Okay, into the distance is 0.02 plus LT into 5.5 equal to 0. Now you see in this equation we know everything except LT. So LT is the one that has been asked. Tail lift force. So tail force is nothing but tail lift force. Okay, the vertical force of the tail is tail lift force. So that's what I have given here. So now if you calculate this entire equation, you will get your LT to be 15.09 kilonewton. Okay, 15.09 kilonewton. Approximately you can write 15 kilonewton. Okay, so everything is known in this equation. So the tail force will be 15.0 kilonewton. This is a very easy question. So we all would have studied the relation between, it's a standard results, the relation between the true airspeed and equivalent airspeed. True airspeed is nothing but VTAS is nothing but from Bernoulli's equation, it's root of stagnation pressure or total pressure PT minus P static pressure into 2 divided by density at that current altitude. V equivalent airspeed is nothing but the numerator will be the same, total pressure at that point minus static pressure into 2 divided by rho naught. Rho naught is nothing but the sea level altitude, sea level density sea level density. If you divide these two equation, VTAS divided by root of VEAS, which is just asked in the question, true airspeed divided by equivalent airspeed, which is equal to it's very straightforward. So the numerator term will go out. So this is nothing but root of rho naught by rho. So the sea level density divided by the current altitude density, the whole power, the whole root. So option B is the right answer, or option 2 is the right answer. Okay. Okay. So this is also one of the tricky question. To understand this question, first I'll tell you, I'll explain the question, then we'll try to understand and get the answer. For a conventional fixed wing aircraft in a 360-degree inverted vertical loop maneuver, what is the load factor at the topmost point of the loop? Okay, assume the flight to be steady at the topmost point. Okay, so what they are doing is the aircraft is flying, they are going to take a 360-degree inverted vertical loop, which means that what the aircraft is going like this and it is going to go like this, it is going to take this path. Okay, it might start at this location, but it is going to take like the path like this. They're asking what is the load factor at the topmost point of the vertical loop, which means this point. 360 loop is like this is the 360-degree loop. At the topmost point, what would be the load factor? So we all know load factor is L by W, right? The definition of load factor is lift divided by weight. But here you have to be slightly careful to understand this. Let's understand this figure. The aircraft has started from here and it is moving. It is taking a vertical loop, and they asked what is the load factor at this point, topmost point. So let's do the force balance at this topmost point, vertical force balance. Okay, if you see the topmost point is little unique because at the topmost point both the lift and weight will act in the same direction. You see here it's not the case. If you see the bottommost point, lift is acting in the opposite direction, weight is acting on the opposite, and centrifugal force is also acting in the downward direction, because centrifugal force will always act perpendicular to the flow direction or flow path. Here the flow path, because the aircraft is in an inverted mode here, right? So here the flow path is in this direction, so centrifugal force is acting in the uh, higher direction or upper direction, whereas the weight as well as the lift is acting in the lower direction at this point. So they're asking what is the load factor at the topmost point of the vertical loop. So this is the topmost point. Let's do the force balance here. L plus W, see, equal to your centrifugal force, which is nothing but mv square by r. So now what is load factor? L by W. So let's manipulate this equation like that. So L by W plus 1 equal to, I have taken W out, commonly out, so that's why L by W plus 1 equal to mv square by R into W, because that W I'm putting it in the denominator, and W can be written as M into G, right? L by W can be written as load factor, that was its load factor. So N plus 1 is equal to mv square by R into W can be written as mass into acceleration due to gravity. So M will go out. So N is plus 1 is equal to V square by Rg, which will implies load factor is equal to V square by Rg minus 1. So this will be a positive number always. V square by Rg will be always a positive number, right? And minus 1 of that will give you the load factor, which means what? From this equation, you can clearly write load factor N is always going to be greater than minus 1, right? When you are doing a steady pull-up and at the topmost point, this point, if you do the force balance, it's L and W will act in the same direction, but not that only in the topmost point it will act in the same direction. See here, W and L are not acting in the same direction. L is acting here, W is acting here. So you have to be very careful. It's asked in the question topmost point. So this is the topmost point. Okay. So now if you see this, this will be a positive number. Any positive number minus 1 will always be greater than minus 1, right? Even if you put 0.05 also here, for example, I'm telling, it is going to be greater than minus 1, right? So N will be greater than minus 1 at the topmost point. So if you see the option 1 is the right answer. N will always be greater than minus 1. With this, the solutions of Aerospace GATE 2021 questions related to aircraft performance is done. Let's see the other topic solutions in the next video. Thank you.
If you like this video, please like, share and subscribe my channel to encourage me. Thank you.